Okay, so now let's talk about proportional plus integral control, or PI control. So this is where we have both a proportional gain on the error and also a proportional gain on the integral of the error from time 0, or basically whenever the control system was switched on, until the current time. So this is called a PI controller, or sometimes known as an ideal integral compensator. And again, we're going to be looking at it in this standard feedback loop. And of course, the transfer function here is just Kp plus Ki over S, where 1 on S represents the integrator. So the first thing I want to notice is if we look at this Kp plus Ki over S, what we can do is we can rewrite this by putting these two terms over a common denominator. We've got Kps plus Ki over S. And then we can factor out the Kp, so we've got Kp times S plus Zc over S, where Zc equals Ki over Kp. And so there's going to be a 0 at, well, when does this go to 0? When S equals minus Zc. So we can think about PI control as placing a pole at the origin, so that's fixed, placing a 0 at some negative real number, which is tuned by the ratio of Ki and Kp, and then an overall gain. So rather than thinking of it as two gains to tune, we're going to think about it as choosing a 0 location and then tuning a gain. And so, well, why would we want to do this? So that's what I want to discuss now. So we know why we want to place the pole at the origin. Basically, then we're increasing the system type. And we have this table that we looked at a couple of weeks ago, basically for different kinds of inputs here, a step, a ramp, or a parabolic, so accelerating input. Depending on how many integrators there are in the system, so a type 0 system doesn't have any, type 1 has 1 integrator, type 2 has 2 integrators, then we're either going to get a constant error or 0 error or infinite error. And so, for example, if we look at a step input, then if we don't have any integrators, we're going to get a constant error of 1 over 1 plus Kp. This is the position error constant, not the proportional gain, K capital P. This, if we increase to a type 1 system, we're going to get 0 steady state error to a step input. And similarly for a ramp input, we'd need to increase to a type 2 system to get 0 steady state error. Okay, so that's why we want the integrator, why we want the pole at the origin. What about the 0? What's that there for? Well, let's look at that by way of an example. So this is an example which you might come across considering, say, thermal transfer or fluid flow between some reservoirs. So lots of these processes, we've got slow flows from one compartment to another, and this can often be modeled as a cascade of first order systems. So here we've got a system 1 over S plus 10, S plus 1, S plus 2. So let's look at what the root locus of this system would look like. So we've got our system 1 over S plus 1, S plus 2, S plus 10. Of course, our poles are at minus 1, minus 2, and minus 10. And again, there are no zeros in this case. So if we mark out our open loop poles in our system on our root locus here, we've got 1 at minus 1, 1 at minus 2, and 1 over here at minus 10. And then we want to draw our root locus. So of course, again, we've got to the left of an odd number of poles or zeros. So here we're to the left of 1. So we're going to have part of our root locus here. Here we're to the left of 2, so we won't have it, but here we're to the left of 3, so we will. So we'll have the root locus going off to minus infinity. Anything over to the left here is to the left of 3 poles. Now we know here we have a pole excess of 3, so there are 3 poles and no zeros. So all 3 poles have to go off to infinity. And how do we know in which directions they go to infinity? Well, remember we can compute some asymptotes. And when we've got a pole excess of 3, we know that 1 is going to be going off at minus 180 degrees, and 2 are going to be going off at plus or minus 60 degrees. And the location of the kind of central point of those asymptotes we just get by adding up the pole locations and dividing by the pole excess. So in this case it's minus 1 plus minus 2 plus minus 10 over the number of poles minus the number of zeros, which in this case is 3. And so that's equals minus 13 over 3, which equals minus 4 and a third. Okay, so we've got our central point is about here, and then the asymptotes are going to be going off at plus or minus 60 degrees, and this is just a rough sketch, but that's going to go up something like that. That might be a bit less than 60 degrees, but you get the idea. Okay, and then the root locus itself is, this one of course is going off at minus 180 degrees, and then these two poles here, they come in to a point which is going to be approximately in the middle. There are ways to compute where exactly this point of departure is, but we don't expect you to know it in this course. And then, so you can just guess that it's in the middle, and then they'll go off towards these asymptotes, something like that. So we can see that in this case, if you were to consider tuning the gain for this, depending on, again, we're going to see you've got a slight increase in, slight decrease in settling time as you increase the gain, but then actually as you increase the gain further, the settling time is going to get worse. The real part is getting closer to the imaginary axis here. I mean, so the real part is getting smaller, the root locus is getting closer to the imaginary axis. The overshoot is getting worse, so that as we go up here, the angle from the real axis is getting larger, but the rise time is getting better. So if here you're going to have some trade-off between improving the rise time. If you go up here, you get very fast rise time, but quite a lot of overshoot and a slower settling time. So that might be the kind of trade-off that you're looking at. However, no matter where you go along here, you're probably going to get some steady state error. So let's say you might choose some particular pole locations up here, and then as in the previous example, you can substitute that value in. You can have a guess at what that value is, and substitute in here and work out what the gain will be. But how would you actually eliminate the steady state error? So let's have a look what happens with PI control. So here we have a system of this form with 3 poles. Now this is taken from the textbook. It's a similar kind of schematic, although a bit more evenly spread on the poles, but we still have this same, the root locus goes off to minus infinity, and then these two come in and then they go up. They're going to keep going up at plus or minus 60 degrees. So let's say we're able to choose a particular gain that placed the poles at some value A, and of course it's going to be minus A as well, the complex conjugate of A. Now, if we were to just place a pole at the origin, so let's say if we had our controller K was just Ki over S, and we didn't have the proportional part, so then all we'd be doing is placing a pole at the origin here, then that's going to totally change the shape of the root locus. Now we've got these two real axis segments. Now actually the asymptotes are going to be plus or minus 45 degrees, and the central point is going to be in the middle here. So we draw these asymptotes here, and the root locus is going to go off like that. And so whereas before we had this point A, which looked like a good pole location for us, now by adding an integrator at the origin, if we just have this kind of just pure integrator controller, then we've totally changed the shape of our root locus, and it's no longer possible to get anywhere near this point A. So what can we do? Well, let's recall that the root locus, the path of the root locus, is actually defined by summing up the angular contribution, so all of these angles here, say theta 1, theta 2, theta 3, and these should all equal some odd multiple of 180 degrees. And we're adding angles from zeros, which in this case there aren't any yet, and subtracting angles from poles. So in this case, that angle criterion was true at this point A, but in this case with the additional theta c, now it's not true. So theta c destroys that relationship. But since we're adding zero angles and subtracting pole angles, if we were to add a zero very close to the origin, then its angle theta would be similar to theta c, and by adding its angle here, things would almost cancel out. So that's what's happening here. Basically, if you introduce, as well as the pole at the origin, you also introduce a zero close to the origin, then we've got minus theta from the pole, from the controller, plus theta from the zero from the controller. And if these are pretty similar, then we're still going to get almost the same root locus that we had before, because their angular contribution actually cancels out, and it's the angular contribution that defines the root locus. So by adding both a pole at the origin and a zero close to the origin, we can actually increase the system type, so we still get our steady state error, without changing the transient response too much. And again, if we look at the example from the textbook, so we have s plus 1, s plus 2, s plus 10. Let's say, in this case, this designer has obviously said that rise time is extremely important and settling time and overshoot are not so important, so gone for a very quite a large gain here. This corresponds, this point on the root locus corresponds to a value of k proportional gain of 164.6. The steady state error in this case we would work out by 1 over 1 plus the overall transfer function, so that's g and k, I guess. So maybe I should put a k here, evaluated at 0. So that's, we've got k is 164.6, and if we put s equals to 0 in here, we get 1 times 2 times 10, so that's over 20, and this equals about 0.108. So this this controller, just the proportional gain, will have a steady state error to a unit step input of more than 10%. However, if we use the PI controller idea just introduced, if we place a pole at the origin and a zero close to the origin, so now at minus 0.1, so that's about 10 times closer to the origin than the nearest other pole, and maybe kind of, you want to be kind of 5 or 10 times closer to the origin. It's about 5 times closer to the origin than where the closed loop pole ends up. So it wants to be kind of fairly close to the origin so that the angular contribution will cancel. So here we see now we've got a gain which is similar to place the poles at a similar location. So in this case, a gain of 164.6, got it about minus 7 plus 4j, and here again almost the same pole location with almost the same gain. And if you look at the closed loop responses, you see that the transient responses are in fact almost the same, whereas if we have the PI controller, the steady state value goes exactly to 1, whereas without the controller, without the integral controller, it'll go to something like 0.9. Now let's have a look at how this system looks in MATLAB using SciSoTool. So again, we can enter in the system like so. We get our transfer function here, and then we just type sysotool G, and that loads up the control system designer interface. Now again, we're doing bow plots next week, so we'll just move this over here, this over here. There we go. So we can just rearrange the windows a bit so that we have lots of room to look at our root locus and our step response. And as you'll see, the root locus looks very much like the one that we sketched, so that's good. We can zoom in a little bit on the region which is more of interest to us, and we can click and drag the poles, and we can see that as we move the poles up along the root locus, we get, as expected, much faster rise time because the magnitude of this vector is getting bigger, but also more and more overshoot. And actually the settling time gets worse. We're moving the real part closer towards the origin. So you would only push up here if rise time was really important. You really need to get away from 0 and up to this region quickly, but settling down to a precise value quickly is not so important. But anyway, let's have a look at the effect of that. So if we choose some poles around here, now we want to place a PI controller. And so what we want is a pole at the origin and a 0 at about -0.1. So you're able to use these buttons up here to place poles and zeros wherever you want. You can also just right click on this root locus, and you can tell it I want an integrator. So that's going to place a pole exactly at the origin. And we notice when we did this, that completely changed the shape of the root locus. Right? So that's actually exactly what we expected. Now we've got root locus going off at these 45-degree asymptotes. So we really need the 0 to be placed as well to get back something similar. So you can actually just visually place it here. We can just click and place a 0 wherever we want. And if I zoom in a bit here, I'm going to move that in a little bit. So I thought around 0. Oops, that's the gain. Move the 0 to about -0.1. See down on the lower right there, it tells me exactly where it is, and so that's about -0.1, and then I can zoom back out. Oops. And now I can readjust my gain, and now I get similar kind of overshoot characteristics, but we see that instead of settling down to a steady state error of about 10%, it's actually kind of slowly converging up, and the steady state error is eventually eliminated.